All right. Good morning, afternoon, or evening, everybody. Welcome to the CSDA Vendor Focus PlanetIQ NASA Commercial Satellite Data Acquisition Program training webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Saving Time, so we're going to go ahead and get started. I will begin today's webinar with just a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat. And you should see that located on the right side of your screen. If you don't see the Q&A panel, there are two ways that you can activate it. You are either going to see a small, kind of what looks like a floating question mark graphic at the bottom right side of your screen, or the three dots in the bottom right corner of your screen to pull up your panel options. And that will be dependent on whether or not you're joining from the desktop application or the browser. Okay. All right. And then just a quick word about the chat. Participants have the capability to chat with the hosts and the presenters, but not all participants. So if you have any questions, again, we'd like for you to enter those into the Q&A panel on the right side of your screen rather than the chat. Also, something to keep in mind, other participants can benefit from those questions if you're adding them into the Q&A panel. So thanks so much for that. Today's webinar is being recorded. The recording will be made available online within a week of completion. And then what I'll do on my end, once completed, I'll send an email to all registrants and participants that includes links to both the recording and presentation slide decks used within today's webinar. As far as timing is concerned, today's event will be 1 hour long with 45 minutes allocated to the presentation and live demonstrations. A 15-minute Q&A period will follow, and depending on the volume of questions we receive, we may extend the Q&A session, but we will have a hard cutoff of 3:15 p.m. Eastern Time. During this afternoon's webinar, we have one speaker from NASA CSDA Program and one speaker from program vendor PlanetIQ. Our first speaker for this afternoon is Dana Ostrenga. Let me go ahead and pull this slide forward a bit here. Dana is the CSDA Program, project manager at NASA's Goddard Space Flight Center. She will begin this afternoon's webinar with an introduction to NASA's CSDA program and its objectives, and then we'll provide a high-level overview of the CSDA program vendor PlanetIQ, its IDIQ contract, and data access. Once finished, we're going to transition to our vendor speaker for this afternoon's event, Dr. E. Robert Krasinski, who is the co-founder and chief scientist at PlanetIQ. He will kick off the vendor portion of today's event with an introduction to PlanetIQ, and then from there he's going to discuss the fundamentals of global navigation satellite system radio occultation, or GNSS-RO measurements. He'll dive from there into a comprehensive overview of the PlanetIQ GNSS-RO data available through NASA's CSDA program. And then what we'll do is we're going to transition to some data use cases. He'll provide an overview of the additional PlanetIQ data products that fall outside of NASA's CSDA program. And then finally, Rob is going to wrap us out today with a future outlook. Once finished, what we're going to do is we're going to open up the final optional polling questions and transition directly into the question and answer period. So before I toss it over to Dana, I'd like to say just a couple of words about this afternoon's Q&A session. We will try to answer all of the questions within the time allotted, but if we are not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. So with that, it is my pleasure to introduce today's first speaker, Dana Ostrenga.
Fantastic. Okay, so let's go ahead and get started. So thanks, Jennifer, for getting us started today with another CSDA webinar series where we're here to learn about our commercial partner, PlanetIQ. I'm Dana Ostrenga, as Jennifer said, the CSDA project manager located at NASA Goddard Space Flight Center. Let's start with why buy commercial data. The commercial satellite industry has been rapidly growing, especially in the area of Earth observations. Commercial Earth observation satellite systems have been developing at faster rates with ever-increasing numbers in their constellations. They're leveraging newer technology, providing higher spatial resolution and shorter revisit rates. making it really ideal to augment our existing government satellite data. So how does NASA fit in? NASA has a strong history of Earth observation data. They acquire, enhance, utilizing, and stewarding that data, and NASA really wanted to explore the possibilities of acquiring and integrating commercial data into our broader suite of Earth observation data to support research and application initiatives. So go into the evaluation portion of our program, that process provides an assessment back into the commercial partners, which improves the interoperability and accuracy of the data, not only for the marketability, but easier integration into our research programs and science applications. If you missed any of our previous webinars, just to give you a little background, the CSDA program serves as the central mechanism at NASA for identifying, evaluating, and acquiring commercial satellite data that support NASA's Earth science research and application goals. The program itself, it has 5 main goals. One is to establish a continuous and repeatable process to on-ramp new commercial data vendors, to enable sustained use of that data for broader dissemination to our scientific community, to ensure long-term data preservation, access, and distribution of that data, ensuring scientific reproducibility, to collaborate and partner with interagency and international partners on the evaluation and scientific use of the data, and to comply with the 2003 U.S. commercial remote sensing policy. You can go to our CSDA YouTube channel to see our kickoff webinar for the series talking more about our program, as well as a list of our commercial partner webinars to date in this series. So this slide just kind of showcases our diverse array of commercial vendors, each providing unique satellite data products to help NASA advance Earth science. We currently have 15 commercial vendors on contract that we can acquire data from. So for multispectral imagery, we partner with Maxar, BlackSky, and Satellogic. Planet operates both in the multispectral and the hyperspectral domains, alongside Teledyne Brown Engineering and Pixel, who specialize in hyperspectral data. Another one of our vendors, Airbus, operates in both multispectral and the area synthetic aperture radar, alongside other SAR providers, which include MDA, Umbra, ISI, and Capella Space, all enabling all-weather day-night imaging. For monitoring methane emissions, our go-to provider is DHDSat, and GNSS radio occultation capabilities come from PlanetiQ, who we're going to hear from today, and Spire, contributing valuable atmospheric profiles. Digital elevation models are sourced from Maxar and Airbus, and for precipitation radar, we utilize data from Tomorrow.io. So together with these vendors, they enable NASA to access high-value commercial satellite data across a broad range of Earth science applications, enabling our science to monitor and understand our planet. So when NASA evaluates commercial data, it provides confidence not only for our science community, but also for the commercial partners themselves. So I just want to highlight a few of those benefits here. First, our partners gain greater recognition within the science and application community. Being evaluated by NASA and our interagency partners really signals credibility. Second, it builds trust with the customers, investors, and partners by showing that the data meets rigorous NASA standards. Our commercial partners also gain access to NASA's deep expertise in data quality, which can strengthen their products and practices. And these evaluations often strengthen commercial partner capabilities. Through CSDA communications, our commercial partners also see increased brand awareness and visibility across research ecosystem. And finally, NASA evaluations bring greater exposure to the full utility of the data alongside the communication of research initiatives from our commercial partners, ensuring it's used to its maximum potential. So in short, like NASA's evaluation process not only assures the science community of data quality, but it also directly strengthens commercial partners' credibility, capabilities, and visibility, not only in the marketplace, but across the federal space. Since that evaluation process plays such a critical role in our program, so I just want to walk you through the data evaluation criteria that is part of that process when assessing the quality and utility of the data. So first, let's look at how easy it is for researchers to search, discover, and download data from our commercial partner systems. If access is difficult, it limits the scientific use. Second, we evaluate the completeness and accuracy of metadata. We know good metadata provides the context scientists need to properly interpret and apply the data. Third, we assess vendor support services, make sure the responsiveness, availability, and technical expertise are there. Support really helps our researchers resolve any issues that they have using the data quickly. Fourth, we consider the usefulness of the data for advancing Earth science. Does it align with NASA's science objectives and fill in important data gaps? And finally, we evaluate the quality of the data itself, things like geolocation accuracy, radiometric accuracy, and calibration, using ESA-NASA evaluation guidelines. Together, these criteria ensure that when NASA brings in commercial data, it's not only high quality, but it's also accessible, well-supported, and able to deliver real value to the science community. NASA and ESA partnered to build a joint quality assessment framework to give confidence in the commercial Earth observation data evaluations. ESA first developed a mission quality framework, and NASA's CSDA program expanded it for other sensors and for it also to be evaluate both data quality and how well it supports research applications. Together, this framework is consistent guidelines for calibration, geometric accuracy, metadata, and validation, ensures NASA can make confident acquisition decisions, strengthens the vendor accountability, and then reinforces the NASA-ESA partnership in advancing the use of trusted commercial data. I just want to take a moment and emphasize a few quick areas in the program that we've been focused on in the last year. So all new business that's brought in is through an indefinite delivery, indefinite quantity process. Our commercial partners compete for task orders under a 3-license tier: public release, U.S. federal government plus, and U.S. federal government. NASA does not prohibit the use of the data as long as it abides by those EULAs. And if you're an authorized user, you can get access to any data as long as it's within one of these EULA tiers. We are also integrating CSDA-acquired data into NASA's Earth Data Search. This makes the commercial data more discoverable and usable alongside NASA mission data. And we're strengthening collaboration across the U.S. government by coordinating purchases, sharing evaluation outcomes, and aligning your data requirements. And internationally, we continue to work with partner ESA on developing guidelines, evaluation methods, and programmatic processes. The CSDA is really focused on expanding vendor participation, improving access to commercial data, and building a strong partnership to maximize the value of the commercial Earth observation data. Now that brings us to the CSDA PlanetiQ partnership. So in October 2023, CSDA awarded PlanetiQ an IDIQ contract under our first RFP solicitation. Through this effort, we launched a ROSA solicitation so principal investigators could assess the utility of the data for science. Our CSDA subject matter experts are now working with technical teams and PIs to evaluate the data and better understand PlanetiQ's data products. The evaluation results will be briefed to headquarters in mid-October and then to PlanetiQ in late October timeframe, with the subject matter expert quality assessment report and the utility evaluation being released in winter timeframe 2025 this year. This is barring any schedule interruptions, otherwise that might be slightly delayed. We also will be downloading the data that's being prepared right now for release through the CSDA Satellite Data Explorer, or SDX, alongside those evaluation reports. If you qualify under the EULA, as I mentioned, you can register for access through the CSDA website. The SDX provides a central web interface for search, discovery, and distribution of CSDA data. So this ensures easier access for researchers and a smoother integration with other NASA data systems. That data that is downloaded will continue to be integrated and available through this interface. And as I mentioned previously, it'll also be added to the Earth Data Search client. So that brings us to the next portion of our webinar. Please welcome again our invited speaker who will talk to you about PlanetiQ, Robert. And I'll stop presenting, and Robert, you can take it and tell us a little bit more about PlanetiQ. Let me try to stop.
Okay. I am Rob Kursinski. I'm one of the co-founders and chief scientist at PlanetiQ. I'm going to give you a quick overview in the next 40 minutes or so about what we are and what we produce. So I'm going to talk about PlanetiQ a bit, fundamentals of GNSS-RO, quick summary of the data we've provided through the NASA CSDA, some case study examples, some additional products, and future outlook, and then open it up to questions. So PlanetiQ is a small company of scientists and engineers with many decades of experience in RO, measurements, instrumentation, and extraction of information and applications dating all the way back to Voyager, which is where I first learned about RO. We work closely with NASA, NOAA, Air Force, Space Force, EUMETSAT, and ESA, and other NWP/research centers, including JCSDA, NOAA, EMC and STAR, NASA GMAO, ECMWF, UK Met Office, and Environment Canada in particular. Our headquarters are located in Golden, Colorado. We recently won the largest satellite weather data award ever, granted by NOAA and NESDIS for $24 million. And our philosophy is to make dense measurements of the highest quality at low cost to enable better understanding, modeling, and forecasting of weather, space weather, and climate. So the three classes of data, I'm going to primarily talk about the neutral atmosphere, RO, with some on the ionosphere towards the end, and a bit on grazing surface reflections that we're picking up and some of the uses of that. I do want to make the point that we do want to know what the customers/PIs want in order to decide how best to focus our resources to satisfy the customer's needs. So just don't be strangers. If you've got questions or ideas, our system is very flexible. So this is a quick overview of the fundamentals of GNSS-RO for those. So let me turn on my laser pointer here. Yes, so it's an occultation geometry. So the GNSS satellites are in orbit around the Earth, high MEO orbit altitudes like 20,000 kilometers. And when our satellite, these are the transmitters. When our satellite is moving around the Earth, it sees the GNSS satellite rise, or in this case, set on the horizon. The GNSS signals go through the atmosphere and they bend. The atmosphere is acting like a giant lens. And so that bending is proportional to the vertical gradient of the index of refraction. And from that, we can derive the index of refraction. And so as our satellite moves around, it sees the signal cut down through the atmosphere. And as you see up here, it's cutting down through and giving you, in this case, a temperature profile up in the stratosphere, then down through the tropopause, and then down into the troposphere. And so what generally happens for numerical weather prediction, this information from the bending and index of refraction is assimilated, and that improves the forecast pressure, temperature, water vapor, winds, and other related variables. And it's the atmospheric data is one of the most impactful global data sets. I'll show an example from Météo France later. I also want to mention that at higher altitudes, when the receiver is still further over, we get profiles of electron density up to the altitude of the receiver. And down low, the water vapor becomes very important, and we can derive profiles of specific humidity. So the key features, RO is an unusual technique. It's a very powerful technique because of its unique combination of features. So it produces balloon-like very high vertical resolution profiles on the order of 100 meters from orbit. There's no other system that can do that of just looking at the gas phase and being able to profile it. It also has very long wavelengths because GPS was designed to go penetrate through weather, so it can see through clouds and any kind of weather. It also has high precision, which is important for weather and also for constraining processes to improve weather and climate models. It has very high accuracy, which is NWP uses it for bias correction, and you can also use it for climate monitoring. It's a very good climate monitoring system. And it can profile down close to with all these features, it can profile down to the surface over any type of surface, yielding complete and unbiased global coverage. A quick summary of our capabilities. This is one of our, I'll show another picture in a second, but this is one of our satellites. We have a receiver that we build in-house that tracks all four of the GNSS constellations, GPS with L2C signals, and later GLONASS, the Russian, Galileo, the European, Beidou, the Chinese system. Our big order with big contract with NOAA just started a couple weeks ago. We're delivering 7,000 neutral occultations per day, 500 of which have the enhanced high signal to noise ratio. The high signal-to-noise ratio is available to NASA. It's just NOAA only bought the lower SNR quality products. It also this contract is new in that it also includes total electron content profiles with low latency. So our fourth through sixth satellites carry thrusters, so we can adjust the orbits to extend the lifetime and get better coverage. So far they're in polar orbits, all of them, so they're giving full pole-to-pole coverage. The data has been validated. It's been used by a lot of NWP centers. A key point here is our receivers are modifiable on orbit within the constraints of the hardware. So the software can be modified, the software and firmware can be modified on orbit. So we've made substantial changes and improved the signal processing. I'll also say a few words. We're now measuring dual polarization, which means we actually are also a precipitation radar of sorts. And the data archive, our first satellite launched, and we started producing data in October 2021. So this has a lot of the similar information. I want to talk about these satellites. One point is our receivers track approximately 100 GNSS satellites at a time. Everything that's in view we track. And we meet all of NOAA's NRT or near real-time specs for SNR and latency. Each of these receivers produces greater than 2,500 neutral atmosphere profiles and even higher ionosphere profiles. I wanted to make a point here about these antennas. So these two antennas, the POD antennas, precise orbit determination, and ionosphere antennas, between the two of them, they see the entire part of the atmosphere above the Earth's limb. So these are low-gain antennas that recover everything in view. These are high-gain antennas with fan-shaped beams that are pointed down at the limb to provide very high signal-to-noise ratio. And these are where the neutral atmosphere measurements are produced off of these antennas. And there's two of them in the front and two of them in the back. And these create a very high SNR and a very wide fan beam, so we can see between the forward and the aft face, and we can see the entire limb of the Earth. This is a quick snapshot of just for one day, showing coverage. The red is from Cosmic and the green is from PlanetiQ, so you can see how we complement the coverage that Cosmic provides. Cosmic is providing something like, I think, 5,000 occultations per day. We're providing 7,000 to NOAA. This is a quick summary chart of the data we've been providing. So the stuff in green, and the green box is data we've been providing to NASA, and the orange is our new proposed on-ramp capabilities that I'll go through in more detail. These two are neutral atmosphere. This is con phase. This is the high rate dual frequency carrier phase and amplitude and the positions. And then this column is the bending angle and refractivity profiles. These are ionosphere products. This is the total electron content, and then this is the high rate carrier phase and amplitude for looking for ionosphere scintillations. And these show the various data rates. You'll see that I don't need to go through all this, but with sort of 100 hertz sampling and very high SNR. And what I wanted to say on this new on-ramping capability, this is an updated version of these two columns here. We've created we've created a new processing system. So it includes these are the same four that are over here, but it also includes the dual linear polarization phase and amplitude for precipitation, and it includes some isolated grazing reflections I'll talk a bit about more. This is the second half of that chart, saying that this neutral atmosphere part, these two columns are neutral atmosphere, but it's also useful for the ionosphere scintillations below 150 kilometers and the sporadic E layers and the grazing reflections. The calibrated TEC also includes the S4 amplitude scintillation and the sigma phi phase scintillations. And all of these capabilities over here are now in here. In fact, they're enhanced. Okay, very quickly, how RO data is processed, a simplified version of it. So when you take a neutral atmosphere occultation, you measure Doppler versus time. Knowing the Doppler and the geometry, you can convert that to bending angle versus refractive radius, which is the distance from the center of the Earth, also times the index of refraction. That gets converted to refractivity versus height, which is a combination of the dry density and the water vapor density. When the water vapor density can be ignored in the upper troposphere and the lower stratosphere, the refractivity converts entirely to the density. So you have density versus height. If you know density versus height and you know the gravity, the pressure field has to be holding up that column of mass up above it. So you can integrate this to get the pressure versus height. And if you know density and pressure, you know temperature via PV equals nRT. Now, in addition, when you have a lot of pressure information versus height, that means you also know the horizontal pressure gradients, which is what drives the winds at mid and high latitude. So when you have multiple RO, it improves the winds a lot. And then in the lower troposphere, you can actually isolate the lower and mid troposphere. You can isolate this term by adding temperature information from a forecast. The altitude range for the refractivity is about 0 to 60 kilometers. And I'll just say the resolution is around 100 meters down to 68 meters at low altitudes and increases to about, or degrades to about 1.4 kilometers in the stratosphere. Quickly, some accuracy curves. This is from my PhD thesis on a paper from 1997. This is refractivity error. This is 0.1%, 1%, 10%, and this is 0 to 60 kilometers. And this is after you converted refractivity to temperature. And one of the points is that it has this range of sort of mid to upper troposphere to a bit above 40 kilometers, where the temperatures are the refractivity and the temperatures are extremely accurate. And it's most likely the most accurate temperatures that exist in this upper troposphere through the lower stratosphere. Some quick examples of temperature profiles just to show off what the capabilities are. These are all from July 5th, earlier this year. This is high southern latitude winter, so it's over the edge of Antarctica. You can see very cold temperatures here in the stratosphere. You can even see a surface thermal inversion right here. This is the troposphere, and then where the lapse rate, the temperature gradient changes, this is the stratosphere. As I said, it keeps getting colder because there's no solar heating, so it gets very cold in here. And so this is the tropopause, that transition in the vertical gradients, which are also known as temperature lapse rates. This is mid latitude. This is low latitude, 13 degrees south, showing a very high and cold tropopause up around 16, 17 kilometers. You can see that what's happened is the thunderstorms have pushed very high up into the bottom of the stratosphere and pulled the temperature down, and that actually generates waves. So we see atmospheric waves all the time above the tropical tropopause. And I've cut this off at about minus 20 C because the data is better used for water vapor when you start getting warmer temperatures. It's not as good for deriving temperature. And this is a high northern latitude for the same period, just to show this is in summer. This one over here is in winter. And you can see the sharp tropopause, sharp transition between the troposphere and the stratosphere. Again, looks like it's pushed up and made that part of the stratosphere cold. Again, you use the lower part of this warmer than minus 20. It's better used for water vapor. Yeah, and one other point, as I said here, you can get the temperature gradient, so you can actually see the atmospheric stability because it's got such high vertical resolution and such high precision on the temperatures. And these are some quick comparisons with NOAA forecasts. This is high latitude, mid latitude, low latitude. This is northern hemisphere, southern hemisphere, just showing it's very little difference. That 1% error would be right about in here, or discrepancy. So that the agreement is extremely high with the RO and the NOAA forecast. There's more variability in the water vapor down here. This is going up from 0 to 10 kilometers. So there's more disagreement down low. By the way, this is how many profiles are. You can see the Antarctic topography getting in the way here and cutting off some of the profiles. Yeah, and this is mid-latitude again, northern, southern. This is low latitude. This is showing two different constellations, GPS versus Beidou 3, and they're virtually identical. So there's very little difference from constellation to constellation. And there is some issue with the negative bias and skew down low where things are pulled off, and that is because of horizontal structure and ducting, and that which I will discuss in a minute. For retrieving humidity, you can rearrange the refractivity equation. So here's refractivity, here's the dry density, temperature, and you can derive the water vapor density. Has very high vertical resolution, 100 meter in the lower troposphere up into the upper troposphere where it's warm and wet. Two general techniques are used, direct method and the 1D VAR, which I'm not going to go into a lot of detail on, but the direct method, basically you specify the temperature from a forecast and then you have the refractivity and then you solve for the water vapor density. These are the kind of precisions you can get. The accuracies are actually better. But as a function of altitude, these are the 1 sigma values on the specific humidity in grams per kilogram. And now I'll show a couple of examples. This is an interesting set of profiles. These are actually Cosmic 2 profiles. There's 5 RO profiles here, and there's 1 Bangkok radiosonde. What was unusual about this one is, there's 5 profiles, but we got one very close in both time and space, which is very unusual to get a radiosonde this close in time and space. And so we take a look at that. And the red, these are the 5 profiles. The sonde is the same. The red curve is identical in all of these, and the RO is the blue curve. And the thing that's amazing about this is the close one. And when I first saw this, I thought this notch here in the blue, which is the RO, I thought this notch was an error in the RO. It was just noise. But then when we compared with this radiosonde, I realized that the radiosonde saw a similar notch, same height, more severe than what the RO saw. And this data was actually quality controlled out of the radiosonde. You have to actually go in and turn off the quality control to see this point. And what it just shows the amazing precision and vertical resolution that the RO has, which is very hard to demonstrate in general because it's hard to get the sondes and the RO so closely located in time and space. But anyway, it really shows off what the RO is capable of in the lower troposphere in terms of humidity. This is the as a set of histograms from different reanalyses, and you can also do this with the climate models. This is the solid red line, the thick solid red line is derived from Cosmic 1 refractivity plus temperature from ECMWF. And we did not use the water vapor analyses to minimize the impact of the NWP biases. And as far as I can tell, this is the most accurate one of the family. And you can see there's quite a bit of difference between it and the other analyses, particularly in this dry end, where the RO is seen can really resolve the transition between the just above the boundary layer and just inside the boundary layer. This is at 2.75 kilometers, just above the top of the boundary layer. And so there are big discrepancies, and you can use these kind of measurements to evaluate NWP models and hopefully improve them. Now, we did this right above the boundary layer because we're working to get unbiased retrievals of water vapor inside the boundary layer, particularly at low latitudes. This is a quick jump over to NWP impact, just to show what the kind of impact the RO can have. This is from Météo France. So this is the RO's percentage of all the data going into Météo France, and this is the percentage of the impact on the forecast and analyses. So about 5% of the data going in, and it's having about 16% of the impact. And then with the ROMEX experiment, which is the radio occultation meteorological experiment, which got momentarily up to 35,000 occultations per day, The RO was made up about 20% of the input, and the impact climbed to 42%. So just demonstrating that the RO is extremely important data type and powerful data type for weather forecasting. Now I'm going to jump to the lower troposphere and boundary layer, which is an area we've been really focusing on, as I'll talk about. We tried to mimic Cosmic 2, in fact, even surpass Cosmic 2 in terms of performance. And the importance of the boundary layer was brought home in this 2017 decadal survey. And the importance is because it's critical for both understanding and predicting weather and climate, and our ability to measure the PBL is quite poor over most of the globe. To get global coverage, you've got to have satellites, but trying to profile the boundary layer, which is quite shallow, is quite difficult from orbit because it's short and it's close to the surface, and it's also frequently covered with clouds. RO has this unique combination of very high vertical resolution, precision, ability to profile in any weather conditions and over any and all surfaces. And so it's well suited, certainly not perfect, but it's quite well suited for profiling the boundary layer globally. And it's really the only system that can profile the boundary layer from space under any and all conditions. So not surprisingly, it is one of the key techniques identified by National Academy of Sciences and NASA for measuring the boundary layer. So I'm going to spend a little bit of a few slides on this. This is just a quick slide showing this is boundary layer top derived from Cosmic 2 for June, October, and this is the same thing but derived from PlanetiQ, and you can see how similar the two are. Cosmic 2 is limited to low latitude, so that's why it doesn't, it's low inclination orbit, so that's why it doesn't show what we're seeing at higher inclinations. Now, this is quite interesting and useful, but we also want to profile inside the boundary layer, which is quite challenging. So here's a particular profile example I use. It's a nice profile that the black, so this is altitude 1 to 6 kilometers and impact height, which has been multiplied by the index of refraction. So the surface is around 2 kilometers in this, using this coordinate system. The black is our data, the blue is ERA5, and the red is the NOAA GDAS result. So there's pretty good agreement actually between the RO and the ERA5. On this particular one, GDAS didn't pick it up, but GDAS often does do well. So but this is an interesting case because you can see the RO can definitely help GDAS, and it can actually help the ERA5 as well. And you can see the vertical resolution, an example of it, because this shift between the two of these is 140 meters, which is easily resolved here. You can also see a surface reflection off of this. This is in the South Atlantic. And this is also an intro to what I'm going to show next. This is versus height, and this is this is really sort of versus time. And the signal is going deeper than this. So in actuality, we're actually not fully resolving how sharp this bending angle is. This is a bending angle in radians, by the way, in this axis. So we're seeing a sharp top, but it should actually even be larger. The bending angle should even be larger. So this brings us to another issue. In the lower troposphere, NWP is rejecting a lot of the RO data in the lower troposphere. And this has to do with a thing called ducting, where if the vertical gradient of refractivity, which is, so this is dN dz, so this is the refractivity, this is the geometric height. If that magnitude gets greater than 1 over the radius of the Earth, you get an effect called ducting. And I'll talk about this more next, but that means very large bending angles. And the NWP system, the bending angles get so large that the NWP calculation of the bending angles actually goes unstable under these conditions. So the NWP systems actually throw away the data when this dN/dz gets within 50% of this ducting threshold. And as a result, they throw away, in this case, most of the data from 50 south to 30 north. This is for January of 2023, so it's southern summer here in northern summer. Here, this thing would flip the other direction if this was northern summer. And again, this criterion is simply thrown away to avoid an instability in the DA. Now, when you get ducting, you end up with a bending angle. You end up measuring one bending angle, but there's a continuum of refractivity profiles consistent with that. So you end up with this fundamental ambiguity when we have these gradients that are so large. And these frequently had happened at the transition across from the moist boundary layer below and the drier free troposphere above. That when you get the really sharp gradients, and they produce really sharp gradients in index of refraction, which can exceed this constraint. So the problem we have is we get this non-unique relationship where we've got one bending angle profile, but it's actually consistent with a continuum of refractivity profiles. And what tends to happen is the estimates tend to be towards the low end, and so it systematically produces negative biases in the index of refraction, which is something we want to avoid. Now, it turns out Josip Aparicio in Canada and Eric Wong at JPL did some work, and if we can measure reflected bending angles, so we get these reflections off of the surface, each one of these solutions, these potential refractivity solutions, actually corresponds with a reflected bending angle profile. And so if we can measure this, we can resolve this ambiguity. We can tell which of these is correct and then pick the right refractivity profile up here based on the corresponding reflected bending angle. And so we've built this very high signal-to-noise ratio system like COSMIC 2, and it allows us to see a lot of reflections. So all these red dots are occultations where we see reflections off the surface. The black dots are ones where we don't see reflections. They tend to happen mostly over land. And so the green ones are ones where we're not sure if we're seeing a reflection or not. And we're in the process of implementing a detection method, reflection detection method, and the Xi et al. Method, which is the one that produces this family of curves to pick out which of them is correct. Now, in terms of detecting ducting, in order to do this, we have to know whether or not ducting is present. And so we, like COSMIC 2, built a very high signal-to-noise ratio system. So when there's no ducting, the signal just hits the edge of the Earth and it stops. When there is ducting, the signal tends to leak around and wrap around the Earth, and you get these very deep signals, which otherwise, if there weren't ducting, there'd be nothing there. And so we have built a detection method that looks at these weak signals to pick out when we're seeing ducting. This is a quick plot of SNRs. We have very homogeneous SNR cover, high SNR coverage, except over the Ukraine war area where we're getting jammed. This is COSMIC 2's SNR coverage. They're a low inclination orbit, so they don't get the pole-to-pole coverage that we get. This also allows us our profiles to probe deeper, and so we penetrate deeper. This dark blue is below 100 meters, penetrating to within 100 meters of the surface. COSMIC 2 is not quite as deep. This is showing the ducting. So this shows four colors. Sorry. Purple means, so this is us versus GDAS, high resolution GDAS, 127 level GDAS. So purple means we don't see ducting and GDAS says this shouldn't be ducting. Orange means we see ducting and GDAS sees ducting. Red means we see ducting, GDAS says there's no ducting. And we see a lot of red further offshore than where there's agreement. Green means GDAS says there should be ducting and we don't see ducting. And we see that sometimes along the coastlines, which may mean, in the Andes case, we might be getting blocked by the Andes, so we can't see all the way down. It could also mean that the ducting is extremely close to the surface, and we're having trouble picking it out. This is, again, another ducting figure. This is October and January. You can see how there's a seasonal shift here. One thing that's and you can see, again, that it's mostly over the oceans. One thing that's interesting that caught me by surprise is We see a lot of ducting over Antarctica in October, and that's actually predicted by ERA interim here. And those are not due to water vapor. There's way too little water vapor. And so these are extremely sharp surface thermal inversions that have to be at least 150 Kelvin per kilometer to be causing ducting. But it's predicted by ERA interim, and we're seeing it. So apparently it's there. And there's also radiosonde climatology that shows that in fact, October is probably the month with most severe thermal inversions. Now I'm going to jump to our second on-ramp, which we just submitted. We have a new processing scheme called sliding window phase matching. A lot of the RO is processed with just phase matching, but the sliding window phase matching allows us to do two-dimensional retrieval. So we have bending angle on the horizontal and impact height on the vertical here. So it's not, you can derive a 1D profile, but there's actually 2D information, and it has a lot of advantages. So I'll just show some quick examples. This is a profile derived. This is the sliding window phase matching, and then trying to pick out the strongest signal to get the 1D profile. You can see there's either ducting or just very large bending angle here, and you can see it showing up in the bending angle versus impact height. So you get this very large and sharp, well-defined bending angle profile. This is, you can see where it is. It's slightly in the North Atlantic. Okay, and this is another one off of the coast of England, and this shows a very important point. If you just do a 1D profile, this is what you get. So the red and the green curves are the 1D profile. The purple curve is a radiosonde off the southwest coast of England. You can see that the radiosonde sees this profile, but you can see the RO is also picking up something here. And what we realized is the beam is sliding sideways. As it's going, this is a rising occultation, so it's coming up. But the beam is sliding sideways, and at this time, it's at a different horizontal position than in this time. And so it's actually providing two different vertical profiles here, because these are different latitudes and longitudes. There's this, as I said here, it's about 5 seconds between these. So there's actually horizontal information buried in this, in the sliding window phase matching results that we have not, we've just come to realize and have not been taking advantage of. Another thing I wanted to show, there's a lot of interest in getting the PBL, the planetary boundary layer top. This is an interesting occultation off of South America here in the Atlantic. And the detection of the ducting is done with this region in here, this range of bending angles. And it's what caught our eye is the height of the ducting is down at this height. But if you look at this profile here, actually this bar is supposed to be up here. This is where the ducting is in this part of the profile. And then when we ran the colors to their extremes, you can see that the boundary layer height is actually shifting as you go from south to north. It's shallower here and taller here. So you can actually we're actually getting a horizontal scan of the boundary layer height through here, which is, again, this interesting horizontal information that we didn't realize was there previously. Now I'm going to say a few words about the polarimetric RO. The signal that leaves the GPS or GNSS satellite is right-hand circularly polarized, so it's a corkscrew motion. But you can break that down on the receiving side into a horizontal and a vertical polarization, into two different linear polarizations. And the reason for doing that is when you have flattened raindrops and snowflakes, the horizontal polarization sees more material and gets slowed down ever so slightly relative to the vertical polarization. And the Spanish pause experiment demonstrated that this indeed works. And this is a particular delta phi profile from pause versus altitude. So, so this is showing the polarized RO overlaying over the NASA iMerge. So the color background is iMerge, which is this integrated multi-satellite retrieval for the GPM mission. And then the circles are the GNSS delta phi, and it's shown at 3 different heights, and then the size of the circle is the magnitude of the phase shift. So red is high altitude, upper troposphere, 10 to 15 kilometers, deep convection. Orange is sort of mid altitude, 5 to 10 kilometers, and the black is lower troposphere, 0 to 5 kilometers. And you can see how well these circles overlay the iMerge product. So it's a precipitation radar, but it's done within an RO geometry, which by the way, makes it very complementary to other precipitation measurements. It's a completely different measurement. So what we did on our last 2 satellites is we put a dual linear polarization antenna on one end of those, and this antenna recovers both the horizontal and the vertical polarization. And this is one day from September 18th, showing 2,368, I think, profiles. So of these dual polarization profiles. So these are, it's a precipitation radar, vertical scan. And this is showing where they're clustering, where we get two profiles close to one another, and the orange is 3 profiles close to one another. And there's one green, which is 4 profiles close to one another. These are within 15 minutes of one another and within 400 kilometers. So just there's interest in looking at these clusters because you can get some more horizontal information out when you can get multiple measurements. This is what it actually looks like. So again, this is the sliding window phase matching. This is bending angle in this axis, impact height in this axis. And instead of showing the strength of the signal here, whenever the strength of the signal is large enough that it's above the noise, we're now using color coding to show the phase shift, the horizontal minus the vertical phase shift. So that's what these colors are showing, and you can actually see a surface reflection here. So, this approach allows you to get the full wave optics retrieval, so the heights down in the lower troposphere. And this is a particularly interesting case where we happen to hit Hurricane Helene on September 25th, 2024. This is the hurricane this is the Yucatan Peninsula in Mexico, Gulf of Mexico. These are the occultation beams, the sliding, and so we sampled through this, and we happened to catch Hurricane Helene, and in fact, these are the occultation points. This is the Yucatan, and this is at low altitudes, which is down here. It's off the side of the hurricane, but as it comes up through, the beam is sliding sideways, and it's caught inside the hurricane. It caught 20. We got a shift of 20 millimeters, which is a lot for H minus V. And so you can see that it's actually probing down inside of the hurricane and telling you what the precipitation is doing inside. And these are 3 pictures. This is a thermal infrared image with our beams laid on top of that. The black one is the one with the that happened to catch the 20 millimeters. And so this is 10 minutes before our measurement. This is the closest measurement to our measurement, and this is 10 minutes after. And you can see there's a lot of convective development here, and this is cloud top. So my guess is we're seeing convection that's forming down lower, whereas the infrared is seeing the very top of the convection at the cloud tops. But it's quite interesting. You can see, indeed, there's a lot going on right where our occultation says there is. One other quick point I'll make is we are also seeing phase shifts in the reflections, which we're suspicious is a function of the temperature and salinity of the surface. So we haven't done much with this, but we're just mentioning it because we're definitely seeing it in the data, because there's no phase shifts up in the atmosphere, but we are getting a phase shift off of the surface. Anyway, the quick points on this is high SNR is critical for the lower troposphere and boundary layer. Also, we're getting horizontal information. It's not just a vertical profile, but the beam is sliding. The vertical resolution is about 100 meters. The long track is maybe 100 kilometers, but the cross track might be as small as 1.4 kilometers as it slides through. Now I'm going to show very quick slides on space weather because I'm running out of time here. NASA has purchased total electron content and scintillations. The sporadic E's are embedded in the high SNR data that NASA's purchased, but they're not extracted explicitly, which we're working on now. And the electron density profiles is something we're working on, but NASA has not purchased any of that. This is just basically showing our TEC calibration is extremely stable. This is over the course of a year, so we've got a calibration system that's very stable. This is the TEC multipath calibration. The signals bounce off of the backsides of antennas and solar panels and come in before they come into the receiver. So you average lots and lots of data, and these patterns start to show up versus angle. And so if you don't calibrate, you get this curve here, which is the blue curve. But when you bring in this calibration, which is, a cut through this pattern, this is the green curve, and the difference between the blue and the green curves is the orange curve, showing the calibrated, so showing how effective the TEC calibration is. And this is a particular cut through the ionosphere in terms of this is the lower part and this is the upper part, and just two examples. On the scintillation side, we do get global measurements, and this is during the Gannon storm from May of 2024. This is the Cosmic 2 coverage, and the Boston College folks looked at our data and found a lot of scintillations, particularly phase scintillations, at high latitudes during this Gannon storm. I'll also say we discovered an issue in our signal tracking, because one of the questions is, why aren't we seeing low latitude? And it was there was a receiver tracking issue, which we fixed. That was causing breaks in the signal tracking. But we now see the low latitude scintillations. On the sporadic E layers, these are very sharp layers. You can see one here in the electron density. They produce this big U-shaped curve in the SNRs. And they're important because they completely change the propagation path of HF signals for communications and over-the-horizon radar. One thing we discovered is that they exist in this sort of 90 to 120 kilometer altitude range, but we saw a lot of them at lower tangent heights, which means they're off to the side of the occultation. And so they're actually at the right height, but the tangent height that's being assigned to them is the height that's being assigned to them is the tangent height, which is wrong. So they're sitting off to the side. And when we include those, we actually see 2.5 times more E sub S. They're occurring 2.5 times more frequently in our data, because we're looking at these lower altitudes than in the classical climatologies that have been produced from Cosmic 1, for instance. So there's just a lot of these things out there. They're occurring in like 25% of our occultations. So in terms of future items, we can produce specific and relative humidity. We've been doing it for research purposes, but not giving it to NASA. If there's interest, we can do that. There's a lot of grazing reflection information. We have not extracted that explicitly. Electron density profiles we're developing, E sub S detection and geolocation with backpropagation. There's also a lot of jamming information here. We haven't offered that to NASA because we didn't think it was of interest, but Jennifer said we should include it because people online might want to know. Eventually, we will add GNSS-RO, but that's a ways off. Anyway, that's the conclusion. We have a very powerful set of instruments on orbit with more coming. They're very flexible and modifiable within limits on orbit. We want to know what the PIs want so we can help decide. That will help us decide what to focus our resources on. And finally, please leave your email in the poll if you want to be informed about PlanetiQ webinars or have further more detailed discussions. And that's it. And that's my, it's just rkursinski@planetiq.com. So
Wonderful. Thank you so much, Rob. Thanks, everybody. So with that, we're going to jump right into the Q&A so that we have enough time here to get to some of these. Okay, so the first question is, hold on just for a second. Okay, the chat is obscuring the view here. I apologize. What is the estimated lifespan of the RO receivers on orbit? And when one of them sunsets or deorbits, how quick can a new receiver be launched to take its place?
That's a good question. So we're still the lifetime of our satellites has varied. We're shooting for 7 years. None of them been up there that long. What we're trying to do is to populate them ahead of time before they fail, so that we have enough that we can um, uh, keep a steady number of them up there. So yeah, so I mean, if we started today, it would take us essentially 18 months maybe to get up into orbit from scratch. But that's why we want to launch ahead of time and keep a steady population of these coming up. So that's my best answer.
Well, thank you very much, Rob. Just looking through here too, I know that Tina was responding to our one of our next questions. Okay, so what is the plan for long-term archiving of the purchased data? Will NASA separately archive the data, or is that archive completely at PlanetIQ? That would be important for long-term climate considerations.
I think that's a question that has to be answered jointly by us and NASA. We're certainly maintaining the archive on our end. But yeah, I mean, when you're talking about really long term, I think it needs to be archived on the government side to ensure it's there for perpetuity.
Yeah, Rob, I can go ahead and answer that. This is Dana. So all of the data that is acquired through the NASA CSDA program is archived in the NASA Earth Data Cloud. And we do that so that we make sure that we not only have a copy that's maintained for those long-term research initiatives, but also so that the data is continually searchable and downloadable alongside our NASA mission data. It just makes it a little bit easier to ensure the credibility for reproducibility of research results.
Okay, well, thanks so much, Dana. I really appreciate that response. Our next question is, how did you calibrate the pro signal affected by the ionosphere, following the same procedure from the PAS team?
Yes, I would say that's what we're doing so far. We're using a relatively simple calibration of just looking. It was on one of the slides, but I went through it very quickly. We just look at the in the altitude range up above where rain and clouds can exist. So we look in the lower stratosphere and basically remove whatever trend is present at those altitudes, and then just extrapolate it down through the troposphere.
Okay, well, thank you very much, Rob. Appreciate that. Our next question is, do you also have precise orbit determination information? Has NASA purchased that for assessment? I'm very interested in looking at the POD and grazing information.
Yes, I mean it's in there. It's in those files. It's in the NASA ONRAP 1 stuff that's already been purchased, and it's in the NASA ONRAP 2 files as well. It's very precise orbits and clocks. So.
Okay, perfect. Let's see. Let's get to the next question here. I am interested in ionosphere EDP products. When will EDP data be available for use? Do you have a plan to release it in the future?
I would say that has to be discussed with NASA. We're developing it for the Air Force, but we can make that data available. So I think I think the PIs have to express interest to NASA, and if there's sufficient interest, I assume NASA would then come to us to purchase it.
Okay, Dana, did you want to add anything to that, or shall I move on to the next question?
Yeah, just that if you have any data needs, specific data needs, we ask that you reach out to the CSDA program so we can document that and take that into consideration when we do data acquisition strategies. It's very helpful for us.
It's also very helpful for us because we want to know where to send our resources.
Yeah.
Perfect. So, as a follow-on to that comment, Dana, should they be reaching out directly to you and or Melissa or to Aaron, or should they be sending an email to the CSDA support email address?
So that's the approach would be to send it to myself or to Melissa Martin, who has been NASA CSDA Program Manager. We will be releasing soon an operational system for tasking in archive data request proposal system. I cannot get the title out right now, but this system will make it easier for people to come in and request acquisition or access to archive or tasking capabilities for many of our commercial vendors. It's a half automated system. It should be pretty efficient. And then that way we can capture a lot of those user needs and get people the data that they need.
Okay, perfect. Thank you. All right, moving on to the next question here. In the PlanetIQ excess phase and bending angle retrievals, do you use the navigation bit information for GPS in GLONASS-RO profile processing? Where do you get such information, and do you plan to release the navigation bit information together with your level 0 and level 1A data? And since that's a multi-part question, if you want to repeat
That's
it.
a good question.
No.
Let's see. In the data that we've sent so far to NASA, I don't think the nav bits are in there. In the new data, the on-ramp 2, we're getting the nav bits a different way. We're getting them from our satellite rather than from a ground network. And I tell you the truth, I hadn't thought about that, but it's a question we can in the on-ramp 2 stuff. I think in theory we could provide it. I think we'll need to talk about that internally and with NASA, but in theory we could provide the nav bits.
Okay, thank you so much, Rob. Let me move on to the next question here. I'm just typing a quick acknowledgement for one of our participants. Okay, moving on to the next question. How many satellites do you have up and coming, and when?
We right now we're in the process of getting at least 2 more up there as soon as possible. We're in negotiations on how fast we can get them up there, and I'm a little bit afraid to say how fast. I'll just take a wild guess and say 18 months. It could be shorter, but I'm not really the best person to answer that. And then we've got some other satellites coming after that are a next generation satellites.
Okay, well, we appreciate your response, Rob. The next question is the PIQ Grazing Reflection dataset independently provided, or is it included in the neutral atmospheric product? And then the second part to this question is, do you apply ducting detection to each case?
Okay. The answer is okay. So the grazing reflections in the first set of data that exists right now, they are sitting in the con phase. Well, what's the equivalent of con phase? The level 1B data. They are in there. But they're not extracted. They've been captured by the open loop receiver. In the on-ramp 2 data, the new data, there is reflection data in there, and it is being extracted. It's being filtered so that you can isolate just the reflected signal. So what was the second part of the question?
Sure. Let me move down to that question here. The second part of the question is, do you apply ducting detection to each case?
Oh, ducting detection. Yes, that's part of the, there is a ducting detection that's put into that, the new PlanetIQ level 2 data files. Those files they have everything, almost everything in them. They're a level 1B, level 2A sort of combined file, also including the dual linear pole and the reflections and the ducting flag.
We've got about 4 minutes left, but I wanted to just remind everybody that we will be posting. I will reach out to all registrants and participants and provide a link both to the recording from this afternoon's event as well as to the presentation slide decks that were used in today's webinar. Okay. So with that, I don't see any additional questions. And just thank you so much, everybody. A giant thanks to our speakers today, Dana Ostrenga and Rob Krasinski, and to the PlanetIQ team for this content. And then also to all of you for taking time out of your day to spend it with us in this data training webinar. We really appreciate you and all of your feedback. And then I would say, thanks to my backup hosts, Geraldine Tuart and Joseph Smith. All right, everybody. So they can address it offline if needed. All right, everybody. Have a wonderful afternoon or evening. All right. Goodbye, everyone.